Recording in progress.
Good day, everyone, and welcome to another interesting session which we are going to have today as part of an year-long series which the IEEE EDS Delhi chapter, New Delhi, India is organizing jointly with the Indiyal Upadhyay College, University of Delhi, under the aegis of the Department of Biotechnology's Star College program. And this particular series is important especially because we are celebrating the 75th anniversary of the transistor invention. And today we have with us Professor Mithun from Electrical Engineering Department, University of Buffalo, New York, USA. And he'll be talking to us today on the topic quantum switching in Y-shaped nano devices. He's a Sunny Distinguished Professor in the Department of Electrical Engineering, University of Buffalo, and is a fellow of IEEE. His research focuses on nanoelectronic, microelectronic, and optoelectronic devices and materials. Special attention in his research is placed on simulation, design, and characterization of nano devices based on quantum well, quantum wires, quantum dots, and graphene. And he has more than 280 publications in refereed journals, 12 patents, 12 books and textbooks, and 16 review papers and chapters in the books. 23 of his PhD students have successfully completed their dissertation, and he was and is a member of organizing committee of many national and international conferences. And you can see his research activities through his webpage. With these words, I now invite Professor Mithun to kindly share his screen to deliver his talk.
Okay, thank you very much. Do you see my screen correctly?
No, you have to just share your screen, sir, again. Yeah.
I think that I just, one more, share screen number 2. Okay. Now, do you see it?
Yes, perfect.
Okay, great. So then let us start. So as it was mentioned that the topic will be switching devices based on one-dimensional electron gas in Y-shaped devices. So I will explain what it means, and this is really quantum devices. And here it's very short outline. First, I will talk about electron waveguide switch, why we do it. Then we discuss simulations of these devices and testing our ballistic waveguide structure. So the quantum devices have very long really history. Oh, and also I will disconnect my video. I think that it might be, oh no, oops. I'm unable to disconnect, it's okay. So it has a long history, and the very first really it is so-called Aromov Bohm interferometer. So you see, while we talk about the quantum devices and waveguides, so you all very well know that electron has really duality or dual properties. It's behave as a particle as well as a wave. So the quantum devices uses the wave property of electrons. So if now you see electron waves is coming, and then the beam split it in 2 parts. And if now we have different paths for electrons on the one branch on the another, then as they meet, they interfere. And this interferometer really can either have the sum of these two, and if they come in antiphase, then you see it will be no signal on the drain. So there are several devices, and the most interesting, for example, this coupler, because if you have current going through one device, then it can couple to another, so it initiate current in the second. So it's wave propagation. So we will talk about so-called Y-shaped device. And as you see, it's got its name from really the shape, because we will refer in the discussion, this is like stem of the device, and these are two branches. And so if we have contacts on the stem and on the branches, then current can go to either one of these two branches. And if we attach gates, and as you see, what is important here, that we have gate on the right side and gate on the left side. They are not connected here, in contrast to some transistors, because it will be one gate that will squeeze the electron beam inside of the device. These gates can help switching the current from one branch to another branch. And here you see it is shown that there is, as electrons are in the waveguide, they have the wave functions, and I will talk about this a little bit. So if they enter at the place before the gates, the lowest quantum states has this symmetric wave function. But if we have voltage applied to the gate, then due to the influence of the electric field on the gate, you will see that wave functions will be shifted to one of the sides during the passing of the wave through the gate region. And so current go to, in this case, like shown that you switch the wave function to the left side, and so the current go to gate 2. So it is shown here, if there is no bias applied to the gates, then of course the transmission is equal to both gates, you have equal currents. But if you shift the wave functions either to the right or to the left, then you see you have switching of the current, and in this case it is shown that it's practically current going completely through one of the branches, and there is no current through the second branch. So the interest in this device is initiated by the fact that switching occurs at the very small voltages applied to the gates, you see, and this is in the contrast to the transistors. For example, if it is MOSFET or other transistor, then the voltage determined by the thermal distribution function of electrons, and really the swing voltage is determined by this simple equation, kT divided by E, electron charge, and multiplied by the log of 10. So if we take 60, we get 60 millivolts per decade, and I explain what is per decade. It means that, you see, it means that if we have room temperature, then we have 60 millivolts to change current by 10 times. So decade is here, it's decrease the current by factor of 10. So as you see here, the estimates for room temperature is 60 millivolts, but in quantum switching, it's only 1.2 millivolts. And the switching voltage really depends on the length of the gate. You see that here, you see that it's possible to show that the switching voltage depends on the velocity of the electrons, Fermi velocity, and the length. So this was really calculated and demonstrated that yes, it's possible to have ratio between the current that will be in off condition and in on and off. The ratio is equal to 10 if we have plus 2.4 volts on one gate and minus 2.4 volts on another gate. So the total voltage applied is 5.8 millivolts. That is 10 times, as you see, less than the conventional transistor. So the modification of the wave function that is shown here, and I will discuss this in more details in calculations, that you see we really modify the wave function, and this is the voltage that is required to move the maximum of the wave function to one of the side of the waveguide. So here it is a comparison of the parameters of MOSFET, like transistor, and quantum wave guide switch. That you see, as I already indicated, that in MOSFET we will have about 60 millivolts for the 1 decade change of the current, the change 10 times. But in quantum waveguide switch, we need only 6. And not only this one, that you see the allowed capacitance for switching is substantially larger, that allows to have more electrons in the waveguide for switching. And also, what is one of the important parameter then energy that is required for the switching, that is the product of required energy by the switching time, that you see it is substantially smaller in the case of the quantum switching. So these devices have substantial interest, and the characteristic that are shown here is really desirable, but not achieved as of today. And this is mostly, as you will see from the discussion that I will present further on, due to the problem how to make these gates. The gate is really the main part of the problem. So the switching power, small, because the applied voltage is small, and also the switching time is shorter. That is why these devices are beneficial for applications. And there are several applications. I will not focus too much on this, because we really produce the device, try to have it high-performing device, but they can be used in the cellular automata, because what is going on, that as electron wave goes through one device, it does not lose its phase, it can go to another device. So you can have like quantum automata devices, and also even some efforts to use the switching for quantum computing and quantum information. Now let's come to the details of simulation of the device. So here you see the Y-shaped device, and we have coordinate axis like Y-axis is along the current, X is in the plane, and Z is perpendicular direction. How we produce the device, it will be a little bit more details when I talk about the processing. But you see, mostly what is going on, that you have quantum well. So you grow the structure in this direction, and this planar structure. So the quantum well that we will use in simulation and later in making the device, it's 10 nanometer thick. And then, of course, you do etching, and the waveguide size depends really on this direction as well. So the quantum wire that is formed from the quantum well has 10 nanometers in this direction, and this we can change by the etching. Most of the simulation that I will show will be for 60 nanometer wide waveguide, and we produce devices from about 80 nanometers to almost 200 nanometers wide. So it is shown here that we use the two-dimensional Schrödinger and Poisson solver to find the wave function and all levels that will be in these quantum wave guides. And the non-equilibrium green function approach is used to calculate the current density in the device. So here is an example for the case when gate voltage not applied yet. So as current propagate in this direction, then as I already mentioned, it will be split equally into two branches. So here it is simulated path, and it shown at z equals 0. Z equals 0 is at the middle of the quantum well. So then at z equals 0, you see that the current start really to split in two beams even before it hit the branches. And this is mostly due to the fact that you see here the separation of the stem into branches. And from this part, it will be reflection of electron wave. So you see here, reflection really influenced the current even before it comes to the branches. So as in this example, you see the current equally splits in two parts and going into branches. Here, the cut is at y equals 0. This is y equals 0 here in the middle of the gate. In the middle of the gate, and current, as you understand, depends on the carrier concentration. So here it is shown electron concentration at this position. And here it is very well, you can see the quantum well that is 10 nanometers wide. Then these are spaces. And these are parts, as we will see in the device that we produce, is really the doped areas. We use doping, and as in quantum well, the energy is lower than electrons from the dopant come to the quantum wire now. And in this case, what is going on, that changing the doping, we can change the concentration inside of the device. And I will show one more example of changing by the gates as it is really done in the conventional transistor. So this is situation without the applied voltage to the gate. But to check that we have reliable simulation of the device, first we calculate the dependence of the current on the concentration of the electrons in the channel. So here it is shown that this conduction band of the semiconductor that is used for the quantum well, this is position of the first level in the stem. In the stem, we have 60 nanometers wide. Here, there are 30 nanometers wide. As here, the quantum wire is wider, then of course the level is lower than in the branch. So now, due to the quantum character of the electrons in the waveguides, we will have current going through the device only when the first quantized level in the branch will be below of the Fermi energy. You see, it is shown here as we increase the concentration when the quantum level in the branches will be below the Fermi level, then we have current going through, and the current really determined by the quantum conductance, and quantum conductance is shown here that this is absolute value, but quantum conductance is really depends only on the universal constant. So quantum conductance, as you see, 2 is square over h. And as we have conduction through the one level only, then quantum conductance depends only on the fact that this first level is conducting, but it does not depend on concentration. As you see here, as we hit this level of G0, the conductance remain constant. As we increase the concentration, then you see the second level in the branch will come below the Fermi level, as you see shown here that increasing concentration we push the Fermi level up, and now the quantum conductance increases, and as we have conductivity through the two now channels, then you see it's a constant again until the next level come below, and so on. So these are quite reliable saturation demonstrate to us that yes, we have correct calculation of the current through the system of the electron wave guide. And now we applied the voltage to the gate. And here there is this figure shows that it's possible to get some more or less reliable evaluation of the switching by looking only on the wave functions. So as we apply the voltage to the gates, positive to one gate and negative to another, increasing the voltage, as you see, we really move the maximum of the wave function either to the left or to the right, depending on the voltage. The high voltage will be applied, the stronger will be the shift. And you see now that this is the lowest level in the branches. And as we shift the wave function, the overlap between the wave function and in the stem and in the left branch, as you see, substantially larger than here, because the here wave function diminishes, the overlap becomes smaller. So here, this slide shows you that we can evaluate the switching by simply calculating the overlap of the wave functions. And as you see, exact calculation shown by the bold lines. And these are just evaluation based on the wave function. So as you see, for lower temperature, the evaluation close to the exact calculation, but as we increase the temperature, then you see the non-equilibrium green functions give, of course, more exact results. But as you see here, at the small voltages, we have practically complete switch of the current between the branches as the voltage below 10 millivolts. If we increase the temperature, then you see that the slope becomes smaller, but still it is substantial switching observed at high temperatures. I mentioned that we did simulation for different waveguides width, and it is shown here that the wider will be the waveguide in the stem region, the steeper is the switch. You see that why it is, because you have more space for the wave function to move. But at the same time, you understand that if we make it very wide, then we lose the quantization in this direction. And second reason is also that we will have substantially more subbands field, and more subbands fields, as I will discuss now, will create an additional problem. So you see here several waveguides that 100 nanometers thick in the stem, like 60 nanometers and 30. You see that 60 nanometers looks like a very nice optimal switch. And if we increase concentration, that more subbands will be filled, then you see switches become not as effective. So here is a single subband case, but if we increase the concentration so that 3 subbands will be filled in the stem, then you see the slope is substantially lower. So the switching is not as effective. Moreover, the simulation demonstrated that the most efficient switching will be in the case that second level in the stem will be close to the first level in the branch. You remember that branch is narrower, that is why the first level is higher here than in the stem. So the reason for substantially better control of the switching is well demonstrated on these 2 figures. You see here it is shown the psi function for the first level. It has maximum in the middle if you don't apply the voltage to the gates. But the second level has asymmetric wave function. So it has 2 maxima. And these 2 maxima really coincide with the positions of the stems. So here the transmission of electrons from the second level of the stem to the first level of the branches will be the most efficient. So this is like the main results that we try to emphasize, that energy bending here really introduced this easier feeling of the level 2 near the transition from stem to the branch. And here the calculations were done like 10 in power 17 doping in the areas that I mentioned to you before, the doped area below and above the quantum well, that equivalent to 510 in power 10 per centimeter square concentration of electrons in the quantum well. So these are device with these parameters. So as we have the concentration that I mentioned before, 510 in power 10, then at switching that is shown here at 10 kelvins, as you see, very effective. Voltages below even 10 volts applied to the gates has substantial switching, so we have factor more than 10 already reduction of the current here in the left branch, so all current going practically to the right branch. If we increase the temperature, then still, I forgot to mention, there's a black line, it's a total current. So as you see, starting from like 5-6 millivolts applied voltage to the gate, you have practically all current is going through the right branch. When we increase the temperature, of course, we need to apply the larger voltage to have switching, but still it is substantial switching observed at 77 degrees. But if we decrease the electron concentration, as you see here, the switching even more efficient, as you can observe here. Smaller voltage is required at 10 Kelvin, and also at 77 for smaller concentration, we have again the substantially better switching in the interval below 20 millivolts of applied voltage. Now I come to the device fabrication and characterization. So as I mentioned before, we have quantum well that is 10 nanometers thick, and two types of the devices were used. One is gallium arsenide based device that you see it is, we start with intrinsic gallium arsenide and grow quantum well of indium gallium arsenide. And second is growth on indium phosphide. So the parameters of the quantum wells are close for both cases. You see, if we have gallium arsenide barriers, then it is about 20% indium added when we grow the quantum well. So indium X gallium 1 minus X arsenicum with X02 will be quantum well, and it will have 140 millielectron volts band discontinuity. What does it mean? That the band in the quantum well 140 millielectron lower than the conduction band in the barrier. Analogous really band discontinuity or band offsets will be in the case of indium gallium arsenide in gallium arsenide barriers. So here we have in the barrier 53% of the indium, but in the quantum well the content of indium is higher, 77%. So it's again in the quantum well the conduction band is lower by about 130 millielectron volts. So more or less analogous structures. The doping, as I mentioned before, was done outside of the quantum well. You see here the spaces not doped in both structures. It's 5 and 5 nanometers wide. And then we have the doped areas. And in the doped areas, we can change the concentration of the dopant. So it is shown here like 5 10 in power 18 per cubic centimeters, dopant by the silicon. And here it's different, but of the same order of magnitude doping. But doping can be changed to control the electron concentration in the quantum wells. So after the structure is grown, then there is a processing that will produce Y-shaped devices. And here it is shown that for these two doping that we have in the structures, 8 and 1.6, 10 in power 12 at room temperature, But if you go to the liquid nitrogen temperature, then you see the concentration will be a little bit lower than at room temperature. But mobility in both cases that we measured while we have these quantum wells, very high in both structures. And of course, at liquid nitrogen temperature, it is higher than at room temperature. But still, even at the room temperature, as I will show, its devices are close to the ballistic. So as the structure will grow, then we do the processing to form the Y-shaped devices. So here stem and here are branches. And there are two types of the devices are done. That is one, and this is the one that practically was used by other researchers in the past. These are so-called proximity in-plane gates. So it means that now gates are separated from the stem just by the vacuum, or really it is the air, yeah? And these are separation between the proximity gates and the channel. That is why applying voltage, to the proximity gates, as they are not touching, they are far away from the, as you see here, it's about 550 nanometer strange that separate the proximity gates from the structure. Then high voltage need to be applied to the gates. Here it is second type of the structure on which we continue to work, because this will be structure for the split gates that, as I will show later, will be on the deposited on the sides of the structure. And to have these gates deposited, as you see, there is a white trench here where the gates will be deposited. So here there are examples of some of the devices that were produced. As you see, we have stem contact, then two branches and gates, and here the photos of indium gallium arsenide in gallium arsenide waveguides and indium gallium arsenide quantum well that are used on indium phosphide substrates. As you see, devices structure are analogous, that you have branches, you have stem, and then here it's shown the cutoff of the structure. There you have quantum well visible, and then we have dielectrics here. And here are a little bit larger area shown that will demonstrate you that contacts attached to the gates, these are proximity gates, and to the branches and to the stem. And the devices were done in this like 3x5 sets, 15 devices per one set of the structure that were processed. So the quality, as you see, of the E-beam lithography is quite high. And here, what we demonstrate first, that we have really ballistic device. And to check that you have ballistic electrons, the following procedure was suggested and used by people after 2001, that if we don't apply any voltage to the stem, and we apply opposite polarity to the branches, so left and right, you see the voltage VPP, opposite polarity will be applied. Here is plus, here is minus. Then if we have diffusive transport, then the electrons will go like this between the two branches, yeah? There is a way path for the electrons. If electrons are ballistic, then you see what is going on, that electron path will be, you launch electron here because here is minus, it should go to the plus, but as it is electron is ballistic, then it continues. It continues to the stem. And the result of accumulation of electrons or electron transfer to the stem will result in the voltage that will be measured on the stem. And this voltage, as electrons are coming, this is negative, will be proportional to the square of the voltages that applied to the stem, divided by 2 mu f, that mu is the Fermi energy of electrons, or really it is proportional to the number of electrons in the structure. So here results for 77 kelvins, and red, then we don't have voltage applied to the gate. You see these are dotted, the dependence produced from this equation using 55 millivolts for the Fermi energy. As we can see, that really very nice parabola here. When we increase the carrier concentration, and I will talk a little bit more about this, that to increase carrier concentration in the device, we can apply to the gate positive voltages on the both gates. So this will be like in the conventional transistors, and I will show on the next slides, dependence of the current on the gate voltage. As we increase the concentration, then mu increases. So here it's 75 millivolts for this gate voltage, used for fitting the measured curve, that is blue. And then we increase more, it's again the like green curve, and the dotted lines are simulation. So it's shown that yes, we have very well pronounced ballistic behavior of electrons. And if you go to 300 Kelvin, then it's not as well ballistic, and that is why it's necessary to improve really the devices that we have, because you see there is also smoothness on the surfaces can influence the electron transfer through the waveguide. So this voltage is referred as push-pull voltage. You see that we have, as I mentioned, opposite polarity voltages applied. But if we apply the same polarity voltage to the gates, then this device will be used practically as a transistor. And what is shown here, that if the applied voltages to the gates is small, then we don't have substantial influence on the concentration. But as we increase the voltage, then we come to the transistor, and here it is shown the threshold voltage for the transistor. It's about at 0.7 volts. It's threshold, after which you see the we have linear dependence of practically current through the both branches, they are equal. So for using device as a switcher, we always need to work at the voltages below this about 0.5 volts. That we don't have change of the concentration in the device, but we have only the switching. And here for the transistor that was shown on this figure, we show now in logarithmic scale the current through the left and right branches in logarithmic scale. And as you see, the current through the gates that we also measured is substantially smaller than current through the device, and these are related to the leakages. So leakage is small. What is going on here, that instead of going to the branches, some electrons will go to the gates, create the gate currents. But as you see, the difference 2 orders of magnitude. And it's again, if we will work at the small voltages applied, then the leakage even smaller. You see that here the leakage is really very small if voltages on the gates are small. So now I attract your attention to the following fact, that we can use the switching in the low voltages here on the gate, but at the same time, we can use this device at the higher current and still use the switching. You see now, if we apply to the left and right gates the same voltage of the order of 1 volt, you see it's a large applied voltage, you have higher current. You see the current will be 2 orders of magnitude larger than the current. Let's maybe see it's better here even. You see it's in microamps. You see about 0.2 microamps at 1 volts on the gate. And now, in addition to these equal 1 volts, we apply shift. We have now full push voltage applied to the gates. And now what we will have, this is the voltage that the same applied to the both gates, here about 1 volt. So if the voltages on the gates are equal, then what is going on, that we have, of course, current going through both branches equally. Now, if we change this VPP on left, we will, if it is positive, then it increases from 1 volts. Then you see what is going on, that now you will have more current going to the left and less to the right. Yeah. And if we go in this direction, so VPP will be negative, then you see we have switching in the opposite direction. What is very important here, that operating points was chosen at the higher current, practically metallic waveguide. So you have higher current through the structure, and you can use switching, applying additional opposite voltages to the structure. So now, as time close, it is shown here some more switches. but it's for the case that if we connect here to the right and to the right and left branches, load resistance, so it is shown that is 1 megohm resistors connected. Then, of course, what is going on now, due to the current that goes through the branches, we apply voltage here, but it will be voltage drop on the resistor. So it means that in addition to measuring the current, we can measure the voltages here. And of course, due to fact that for different currents, you have different drops on the resistor, you can measure the, instead of current, you can measure the voltages on the left and right stems. Now, this is the main things that we are focusing on now, that using this kind of the gates as we produce and demonstrate the devices are working, you see, we have electric field applied between the gates, but due to the separation of the gates from the device, really from the channel, you have substantially larger voltage that need to be applied. Substantially better will be if we will have like MOS structure, that it is semiconductor here, then will be oxide and the metal. So instead of oxide, it's possible to use even high K dielectric or high K oxide. Then it will be thinner and gates are really close to electron gas. So the voltage will be substantially smaller. So we developed and used this deposition from the side. It is shown here, first the cartoon that you see first. You see if this is the structure, these are trenches, and then we use deposition from this side. The beam is coming under the angle. Due to the shadowing, you see there is no deposition of the metal will be here. Now, after, if we deposit the electric, it will be oxide, and then deposition from this side, then as you see in the important region for us, the gates are separated by the dielectric, and you have left and right gates. And so here it is the structure that was used for deposition. You see that you have deposition under the angle. And next, show the image of the structure. And as you see, metal layer deposited under the angle. You see, first, this is the dielectric deposited perpendicular. The metals deposited under the angle. So this is the first deposition, as you see, green. Then we have blue deposition of the dielectric, and we have deposition of red. As you see now, the red and blue are separated by the dielectric here. So these are produced, but we need to refine the procedure, the deposition, the etching, the use of the dielectric. So here where we are now. And so to summarize what I was talking about, I show you that the simulation claims that the most efficient switching will be in the case when the second level in the stem coincide with the first level in the branches, then it's the most efficient. Then also what we demonstrated that we can use really switching for the higher current when really many subbands are filled. And at 77, we showed that practically under 1 microamps switching was observed. And we developed and used the deposition under the angle to get gates closer to the waveguide. And this is a team of the 2 universities that it is our university at Buffalo, SUNY. At the second SUNY school is really SUNY Poly, that is in Albany. And here is myself, my student. And then from the SUNY Poly, the team of the Professor Oktyabersky, and they have grower and also characterization person specialist. And this work was supported by Air Force grant with program director Ken Garrett. So I think that at this stage, I may ask if there are any questions. I will be glad to address those.
Thank you very much, Professor Mithun, for enlightening us about especially this new branch of devices, which I think many students, they may not be aware of. And there are a few questions which have been shared by the attendees. So I'll just share my screen and I hope it's visible to you.
Okay, I closed my screen so you can show. Okay, lens limitation makes separation of serial. Lens limitation, separation of serial and photo effect difficult. I really don't understand that is length limitation. Length limitation in which direction? Either in direction of the current or the width of the waveguide.
Yeah, I
Because
think it is related to the length direction. That's what I assume.
Yeah, if it is the length direction, then I think that in our simulation and in our really device etching and characterization, we demonstrated that there is no problem with the limits in the length direction along the stem. Because we used, as I can show back, but you have those now recorded, that it is from 200 to 300 total nanometers, total length of the devices. And that can be made shorter in our lab. I think it's no problem. And also, you see, field effect transistors of the same sizes as we used in our devices really were demonstrated and used. So it should be no really problem. What is the effect of different doping to different region of changing thickness of the well and change the width of the dope? Oh yeah, but this is conventional. It's so-called remote doping. So of course the concentration in the well will depend not only on the level of the doping, but also on the width of the barrier between the doped region and the quantum well. This really very well addressed in the literature. So you use optimum, you see, if you move doping area far away from the channel, then of course you see the smaller number of electrons will go into the channel. So you optimize. We use like 5 nanometers, as I mentioned, the barrier between the doped region and the channel, and it give about 80% of electrons transferred into the channel. Can this design be useful? Yeah, it's a good question. You see, can this transistor design be useful for terahertz detections? Detection. Now I will think about this. Really, that this transistor we would like to, and initially we start to work in these devices because the switching time is very short. So it's really very fast device. So using for terahertz detection, I don't know. We never thought about this. You see that I don't see. Yeah, it's interesting. Yeah. No, I'm not ready to answer this question. If you look on my website, you see we have substantial efforts on terahertz detection and terahertz emitters as well, based on graphene. So there are some advantage of this material, and we use it heavily. But mostly what we focus on, and also in the past I worked on terahertz detections. But what is going on? Even if, if I elaborate on your question, if I apply terahertz signal to the gates, and even if it will be really fast switching between the branches, you see, I need then very fast measurements devices that will allow me to measure these changes. What mostly we work on, it's really how to transfer the terahertz signals into the DC. So you measure DC response proportional to the signal. That is the one way. The second, that we were working on semiconductors, this really heterodyne detection. Heterodyne detection will allow us to use the signal that we would like to measure, and then the local oscillator, and the difference in those frequency we try to have in gigahertz frequency. Then we can measure that. Yeah. So I don't know if I answered the question, but I think that the main direction, at least in our work for the terahertz detections, is really to measure DC response of the device. Okay, then it's the easiest way. What are various effects of opposite bias voltage that are applied to the branches in waveguides? What are the various effects of opposite bias voltage to the branches? I will move now this to the branches. There we did not discuss this, that we will have, you see, the opposite bias voltages were applied to the branches only to characterize that these, or to demonstrate that these structures are ballistic. But if you use device operation, and it's obvious, if you apply the different polarity to the branches, then of course you will have different currents. So it's not the goal of the waveguide structure, yeah? Because it's obvious that if, for example, I will apply voltage only to one branch, then the current will go on through this branch and so on. So I don't understand exactly what is the goal to apply opposite biases to branches, because you immediately switch the signal, yeah? So the idea was really to switch signal by gates. I don't know if I answered the question, but I tried it. Okay. If anything else, Dr. Saxena.
I'll just check. I don't think so. There are any more questions which are there. Thank you very much, Professor Mithun, for taking out your time and enlightening all of us, and especially a big thanks to all other co-panelists. Professor Massimo and Professor Michael Ostling has also joined, and they'll be having we'll be having subsequent talk in this particular series by Professor Michael Ostling and other speakers also. So on behalf of IEEE EDS Delhi chapter and the other organizers, I would like to thank you once again, as well as to all the attendees who have joined us today to attend your particular session. Thank you very much.
Thank you really very much. Thank you very much. And I wish you success. Thank you. Bye.
Thank you. Bye-bye.